Hi guys, so this will be your video for antiderivatives and indefinite integration. So this will be your first topic in our last big idea of the year, which is integration. What you need to think about is that integration is almost like the opposite of derivatives, differentiation. So when you're working on this, try to relate what you know about derivatives to integrals, integration. Okay, so here we go. So I put both of these PDFs on your Google Classroom so that if you wanted to either print them out or copy them down and follow along, there will be a lot of problems that I do not do with you during this video that you could do as practice. About midweek, I'll put up the solutions to those problems to make sure that you're on track. So let's break down some of the words and the vocab that you're going to be seeing through this. So I kind of mixed up the pages of the two PDFs so you'll be able to tell the difference between the two. So the first one that I wanted to talk to you guys about is, what is this word of antiderivative? So what you need to think about is anti is kind of like the word like opposite, or the opposite of, and so it's going to be the opposite of taking a derivative. So if you can remember what steps you took to find a derivative, doing them in the opposite way is going to help you find what's called the integral or the antiderivative. The notation that we use is a capital F. So you can see on here we have a couple different notations for F. We have F, a big F to the prime, and a little f. They're going to be equal to each other. Okay, so that the reason that is capital F, so just big F, that is the antiderivative. Okay, so big F represents antiderivative. When you take the derivative of that, it should get you to the function that usually you're going to be starting with. Okay, it's going to be weird. It's going to feel like you're doing everything backwards, but I promise you it gets easier as you move on. So just so you can see the words and the notations. So you can see on here, we have a symbol. Okay, so this new symbol is our integration sign. It's kind of like when we were doing limits, we always wrote limit in the front. When we were doing derivatives, we would have ddx in the front. Now that we're doing integrals, that sign is telling us we're taking the integral. It's kind of like an operation. So we see that we have our new symbol. We have all definitions on here, and this is also on your Google Classroom that you can go through. I'm going to skip the example on this first page because we're going to take a couple notes, then do a couple examples on our own. So you can look at that on your own when you have time. So integration, let's look at, we're going to skip the formulas for right now. With formulas, I guess it was the third page. So looking at this page here, you can see that it looks very similar to our differentiation rules, but in reverse. For instance, if I were to look at this first line and we were talking about derivatives, it would tell me if I took the derivative of x, I would get 1. And that's what it tells us. Over here, if I were to take the derivative of kx, where k is like a number like 2, so like 2x, the derivative of that would just be 2. So you can see how they're linked together. We've already been practicing this one where you add 1 to your exponent and then divide by that same number. So go through this. You can copy these down. You can put them on a note card. They're going to be useful for you because they're basically what you're going to reference until you have it down pat. All right, let's go back to, let's look at it's the STEM Garage worksheet. Okay, on the top it says Math Calculus worksheet. So this is going to go pretty much very similar to how you're going to be doing this on your own. So some things that I've already filled in just so we can talk about it. And we've already have talked about this, how capital F, so big F, is the antiderivative. When you take the derivative of it, you should get little f, which is usually what you guys are starting with. So thinking of the word antiderivative, like the opposite of derivatives, the opposite of what you would do for a derivative. So if I think, and I kind of like brainstorm, to find a derivative, what I would do is I would subtract 1 from the exponent, and then I would also multiply by that same number. So multiply exponent in front. Okay, that's like the basic power rule, right? We would take 1 away from the exponent. We'd also multiply that exponent down to the front. So we're going to do the opposite. So for instance, for a, if I'm looking, my exponent is 1. So instead of subtracting 1, I'm going to add 1. Then I'm going to divide by that number. So you can see on here, I added 1 to get a degree of 2. Then I divided by 2, and then I simplified to x squared. Okay? And this is actually missing one important piece. The one piece that we always have to tack on is that there could be some constant that we just don't know. So you always have a plus c. Let's look at b. So b, we have x to the first. My exponent was already 1. So I'm going to do the opposite of what I would do to find a derivative. I'm going to add 1 to my exponent and then divide by that new number. Okay, so I add 1. Now I have a degree of 2, and I'm going to divide by 2. You could leave it like this is perfectly fine, or you could write it like 1/2 x squared. So thinking about the steps that we're taking, it's the opposite of what we did for derivatives. So we are adding 1 to exponent, then dividing by that same number. We're going to call it your new exponent. That's a way to think of it. So that's how we worked on these problems. You can see it again in part C. So my exponent was 2, so I'm going to add 1 and then divide by that same value. So I got 3, so I have 3x cubed over 3, which becomes x cubed. So let's do one more together. Let's do example F. So just like with derivatives, sometimes we have to rewrite. You have that same problem with integrals. Sometimes you have to rewrite them. So we know that I could rewrite this as x to the negative 2. Whenever you have a denominator, an exponent in your denominator, it becomes a negative exponent. So I rewrote it. Now I can use that same little steps that I told myself. I'm going to add 1 to the exponent and then divide by my new exponent. So that means that now, and I'm going to do this like a really broken down version for you. I'm going to have x to the negative 2 plus 1, and I'm going to divide by that same number, negative 2 plus 1. So I really end up with x to the negative 1 divided by negative 1. We need to keep simplifying. You don't really want to see a negative exponent as part of your answer. So I know that the negative 1 on the bottom just makes the whole thing negative. And the x to the negative 1 puts it underneath of 1. I don't need to write the 1 anymore because it kind of just goes away. So that's our antiderivative. And then remember, always tack on that plus c. I forgot that up here on b and c. Okay, so you always need that plus c. That's a constant. Constants we know when we take the derivative, they go away. So when we're trying to find antiderivatives, we don't really know what number went away. So you need to make sure you leave a space for it. You need to call it a c. Later on in this lesson, we'll talk about how we can find the value for c. Okay, let's do one more of these together. We're going to do a trig function. So let's look at I. Okay, so looking at I, we're looking at the cosine of x. So that means that we had a function that when we took the derivative gave us cosine of x. So when we think about it, if I had the function sine and I took the derivative of sine, I would end up with cosine of x. So that's going to be my antiderivative. So I have sine of x plus c. Remember, that's important on there. And that's because if you think about it, if you take the derivative of sine, you will end up with cosine. Okay, so trig's a little bit easier than you would expect it to be. Think about what would have given me cosine as a derivative. That's going to be my integral. Okay, so we're actually going to be skipping parts 3 and 4 on this worksheet. So do not worry if you don't have responses for them. You don't need part 3 or part 4. But let's look at these basic integration rules. All right. So we have 2 different rules kind of explaining the same thing, but in opposite ways. So our first rule is telling us that integration is the inverse of differentiation. And what that's showing us, it's similar to how square rooting is the inverse of squaring, when you take the integral of a derivative, you end up with that original function. So if we're looking at this first line, I'm taking the integral of f prime, right? That's a derivative of f, big F. And you can see that my result is just big F. Down here, it's the same idea but opposite. Now it's if I take the derivative of an integral. So I'm taking the derivative of the integral of little f. They're canceling out, and my answer is just little f. So that's how you can see how they are inverses, kind of like squaring and square roots. Using these, we have our integration formulas, which are directly from your differentiation formulas. They're pretty much the reverse. Okay, so I am going to go back to that second page that I showed you. So on this page, I already have a couple done for you using the rules that we're already familiar with. So solving these equations, right? Whether or not the direction says solve a differential equation, or on the next slide I'm going to show you, it just says to find the integral, your steps are the same, okay? So you're finding the integral. For instance, I have two completed for you. I have y prime equals 0, so you have to think, when I took the derivative of something, what would give me 0? And that's a constant. We don't know what it is, so we use C. You can see we used our same rules for part B, where you add 1 to your exponent, divide by the same number. Now, the tricky part comes along when you have a constant. So we had a 3. So that means that it was x to the 0 power. So I'm going to have 3x to the first, because that's 0 plus 1. And then divided by 1, which you don't have to see, you don't have to write it. So whenever you have a constant and you're taking the integral, you actually are kind of like adding another x on there. So if you don't see an x, you do end up with an x. Okay? Let's erase that. Let's do one more on this page. Okay, let's do a trig, not too crazy trig, so we'll do D. So when you're looking at this, this is already the derivative. So if you think about it, what would give you cosine as a derivative? And the answer would be sine. We had talked about that. So it's going to be 4 sine of x. Now for my second piece of my function here, I have a negative 3 sine of x. So I have to think, what would have given me negative 3 sine of x as my derivative? And that would actually be a positive 3 cosine of x. The reason why is the derivative of cosine is negative sine. So sine, like SIGNs, positives and negatives, are very important. So plus 3 cosine of x. We do still need a plus c. We don't have that value yet. And that's that. Okay, so there's going to be a lot of other example questions in these two PDFs that you can practice and you can try and you can ask me questions. I'll post the I'll post the solutions probably on Wednesday of this week so you can make sure that you're on the right track. There'll also be a separate video on specific particular solutions. So actually finding what that C value is. So if you have any questions, feel free to email me. Pause the videos, go back, look up different material, but let me know if you need help. Practice problem.